Hi everyone. In today's video, I'm going to go through irrational numbers, including surds. And I know that we've been dealing with these before, but we're going to be sort of more looking at simplifying them. And finally, we're also going to go through adding and subtracting surds. So I'm going to go through a couple of exercises today. You should find this fairly straightforward compared to what the topic you've just been doing, which is looking at quadratics, including the square, etc. So I'm just going to get straight into this, and I won't spend too long on it, but I will be going through two exercises. Okay, so we're going to be looking at deciding if something is irrational, and we're going to be simplifying surds, and we'll look at expressing it as an integer as well, so going back in reverse. So look, there's a little bit of theory for you, but let's get started into looking at the real number system now. All real numbers cover all of the numbers that exist. And of course, we know that we've got all of the integers, so we've got the positive and the negative integers. But of course, and then we've got all of the, so that includes the whole numbers, and sort of the natural numbers are our positive values, and then the integers includes all, both positive and negative. But then we've got the rationals. So for example, we've got all the fractions, so you could think about 1/2 going here, and 2/3 going here, and so on and so forth. But what makes up the rest of the real number plane is all of these irrational numbers. So things such as pi would be irrational, square root of 2 is being irrational, and what they are, we sort of like looking at, if you've got like this non-recurring decimal. So for example, if I was to go and press pi, then that's going to be, if I can recall, pi would be 3.14159.265. I can recall probably up to about 15 decimal places, I'd say 89793, I think it is, and we could keep going on and on forever. As you can see, that they're not recurring. So this is what we call an irrational. Pi is an irrational number. Same thing if I was to do the square root of 2. If I was to do the square root of 2, I'm going to get something along the lines of 1.4142135, and so on and so forth. That's about all I can remember from square root of 2. But as you can see, that these are not recurring. It's so that's usually a hint that it is irrational. So can I place minus root 5 and root 17 on the number line? Well, the square root of 5, well, we know that the square root of 9 is 3, and the square root of 4 is 2. So it's going to be somewhere between 2 and 3, most likely closer to 2. So if I did the square root of 5 in a calculator, it's about 2.236, but it's not a recurring decimal, 2.23606, and so on and so forth. That's going to usually be a hint that this is an irrational number. Okay, so the square root of 5 is sort of negative 2.23. So we're going to sort of say it's probably around about here, negative the square root of 5 I'll put in here. Square root of 17, the square root of 16 is 4, square root of 25 is 5, so it's going to be just a little bit after 4, and to be precise, if I was to do the square root of 17, that's about 4.12 roughly. Okay, so if there's 4 and there's 5, the square root of 17 would be around about there. Okay, now let's just quickly answer some of these questions. A number that can be expressed as a fraction is a rational or irrational number. Well, fractions are rational numbers, and they form part of the real number system. And these irrational ones are these surds and square roots and pi. A surd is an irrational number that uses the root symbol. Okay, so we're looking at simplifying some of those today. The decimal representation of a surd is a terminating, recurring, non-recurring decimal. Well, it certainly doesn't terminate. It's a non-recurring decimal. And now root 25, is it a surd or a rational number? Well, let's think about it. You may look like a surd because it's in the square root, but the square root of 25 is equal to 5. And technically, that is actually a rational number because we can express that as a fraction, like 5 over 1. So this is an example. If it's simplified, it actually doesn't mean it's a surd. It can be simplified. It can be a rational number, like so. Okay, now let's have a look at this. If we want to express each of these and decide if it's rational or irrational, well, if I do negative root 3, that's going to be around about 1.7, negative 1.7320508, and so on. Well, we could locate that on a number line, but is it rational or irrational? It's irrational. 137% is the same as 1.37 if I divide it by 100, which of course, that has recurring zeros, so that would be rational. It could also be expressed as a fraction if you like. We could express that as a fraction of 137 over 100. Okay, so it's certainly going to be rational. 3 over 7, well, rational means that it can be expressed as a fraction, so that's 0.428, etc., etc., etc. But what you notice is if you put this in the calculator, 0.42857, 1, and then look at this, 4285714. You can see there that it's sort of repeating. After we get to here, we're sort of repeating. So it's this sort of recurring decimal. So this means that it's also rational. Any fraction, anything you express as a fraction that's not simplified is also rational as well. Okay, now let's have a look at start simplifying these. Now, when you're simplifying these, the hint that I give you here is that you really want to be looking for perfect squares. You want to be looking for 4, 9, some factors of 4, 9, 16, 25, 36, and so on. So you could actually simplify this. Well, which is the biggest perfect square which goes in here? Well, you could go 4, but in actual fact, 16 goes into 32. So I want to write it like this. That's the same as the square root of 16 times the square root of 2, okay, is the same as the square root of 32. But the square root of 16 is equal to 4, isn't it? 4 squared is 16, so the square root of 16 is 4. So if to simplify that, that would become 4, and then of course that's just 4 root 2. Now, are we done? Yes. Well, we don't have a perfect square which goes into 2. In fact, that's a prime number, so we just stop there. So when we get over to here, when I've got this 3 times the square root of 200, let's think about a perfect square which goes into 100. Well, the square root of 100, that would be the same as the square root of 100, times the square root of 2 would be the square root of 200. And, of course, the square root of 100 is 10. 10 times 3 is 30, so that is the same as writing 30 times root 2, but we don't need to write that times, do we? Just 30 root 2. Now over here we've got the square root of 40. Well, which is the biggest number over here which goes into them? Well, 9 doesn't go in, 16, but 4 does. So let's do that. That's going to be 5 times the square root of 4 times the square root of 10 over 6. Now, let's go ahead and simplify that. Now, the square root of 4 is just 2. So 2 times 5 is 10. So that's going to be 10 times root 10, or just 10 root 10 over 6. But we can simplify that, can't we? Because we can divide the top and the bottom by 2, which is going to give us 5 root 10 over 3. Both of those are prime numbers, so we can't go any further. All right, now I'll get you to try the following. I'm going to get you to pause this, have a go at these, please, and I'll go through them shortly. All right, so I've got you started here. So with this first one, square root of 20, well, we've got to find the biggest perfect square, which is a factor of 20. So we're going to take 4 out. And when I take 4 out, so 4 times 5 is 20. So that means that the square root of 20 is the same as square root of 4 times 5, but the square root of 4 is 2, so it's just going to be 2 root 5, and we are done. Over here, 300 is the same as 100 times 3. 100 is 10 squared, so that's the square root of 100 is 10, so that's going to be 2 times 10, if you like, times root 3, and 2 times 10 is 20. 20 root 3 is going to be our answer. Now over here, the square root of 27. 27 is 9 times 3. Square root of 9 is 3 though, so I'm going to have that's 2 times 3 outside of root 3, and then I've got a 3 on the bottom. Now we're multiplying everything, so these 3's are going to cancel, so what we're left with is just 2 root 3. Okay, and finally, over here, when we've got the fractions, well, the same thing, if you've got a fraction of square root, then we could break this up like so. So we could actually break it up as the square root of 25 times the square root of 5 on the top, and the square root of 16 down the bottom. Now, on the left-hand side, the square root of 25 is just 5. So that's going to be 5 root 5, and the square root of 16 is just 4. So we can just leave it like that, 5 root 5 over 4. Okay, now we can also note, we can also go the other way. It says express these as a square root of a positive integer. So if you think about it, if we usually can bring, like the square root of 4 would be 2, and I want to bring that out the front, well, what I could do is the square root of 2 is the square root of 4. So I could replace that 2 with the square root of 4. And technically, what we can do is just sort of go the other way. Now, the square root of 4 times the square root of 5 is the square root of 20. So there you go. That's our positive integer. Our positive integer is the square root of 20. And over here, that would be, well, the square root of 49 is 7, times that by the square root of 2, which would give us the square root of 98. Okay, so if you have questions like that, then that's how you do those ones. Now, we'll get you to do some of those a little bit later, but I'm gonna because these shouldn't take too long, I'm going to go through adding and subtracting surds. So we're going to look at surds. First of all, if you can simplify surds, you can then add and subtract them, and we're going to simplify them and add and subtract surds. So like surds are the ones which have the same surds. So for example, root 3, you can see there that we can actually, those are like terms. Okay, so if we have these sort of the same thing as well, I can simplify this root 75 to a like surd because I can get that into root 3. Well, how can I do that? Well, first of all, if I had 2 root 75, that's the same as 25 times 3. Okay, and of course the square root of 25 is 5. That comes out the front. 2 times 5 is 10. There you go, 10 root 3. So 10 root 3 is actually, like I said, that is like. Okay, so like terms are those which have the same surd. So square root of 3, if you see another square root of 3, then those are like. And that's what we do when we're simplifying, then we're looking for like ones. So first of all, we want to simplify these, but these are already like. So this is as simple as fact, well, I've got 2 root 3s and I have 4 root 3s. If I add them together, I have 6 root 3s, don't I? Okay, it'd just be like if I had 2x and I had 4x, then I'd have 6x, wouldn't I? It's no different. Now over here, we're grouping. So what you're probably best to do is sort of group these together. So we've got 4 root 6s and I'm taking away 3. I've got 3 root 2s and I'm adding 2 of them. So that's, simplify that. That's going to be 4 take away 3 is 1 root 6, but we wouldn't write 1 root 6. We'd just write root 6 like so. And then we've got 5 root 2s, so 3 plus 2 is 5, and then we've got 5 root 2s. Now, I'll get you to try these, but just remember that we might need to simplify these. Or actually, I'll do these ones with you. So when we've got to simplify, what we tend to do is we want to find like surds, but we have to actually find these perfect squares. Now, of course, 2 squared is 4. 2 squared is 4, and 3 squared is 9. We want to find all of these perfect squares. 16, and we'll sort of go all the way down to, 10 squared is 100. Okay, and we'll keep going if we need to, but often you won't need to go too far past 100. So what we're going to do is, 5 root 2, that's a root 2. 2 is a prime number, so we're sort of going to leave that. But 8 is 4 times 2. So we can simplify that to being 5 root 2 minus, let's bring the 2 out the front. So root 8 is the same as 2 root 2's. And now you can see that we can bring those together. 5 take away 2 is 3. How many root 2's do I have? I have 3 root 2's, like so. Let's simplify this one now. What's the biggest perfect square which goes into this one? Well, we've got 4 times 5 is 20. What's the biggest one which goes into this? Well, we're looking at 9 5s are 45. 9 times 5. So we're looking at for those perfect squares. Over here it was 4. Over here on the right, we're using 9. Now, as you can see, we now have got these root 5s, but let's simplify them now, because the square root of 4 is 2, so bringing that out the front, 2 times 3 is 6, so it's minus 6 root 5. And then the square root of 9 over here is 3, so 3 times 6 is 18, so it's 18 root 5. Now you can see that all of these are like terms, they're all the same surds, so we've got 18 plus 2 is 20, take away 6 is 14 root 5. Okay, now it's your turn to try. Just remember, you need to use the perfect squares. For this one over here, you'll need to use the perfect square of 4. For this one over here, you'll need to use the perfect square of 9. Can I get you to try this now? Pause this now, have a go at this, and see how you... Alright, so the one on the left-hand side, we're looking at the square root of 8 is root 4 times 2. Square root of 4 is 2, so bring that up front. And then we've got 7 root 2 take away 2 root 2 is 5 root 2. The one on the right, just remember, it's actually quite ironic that 2 root 27 is actually the same as 3 root 12. I'll show you why. Well, because if I was to do the opposite, the 2 squared is 4, so if I was to bring that inside, if I was to have, that would be the same as 27 times 4, and the square root of, 3 squared is 9. If I was to bring that inside the square root 12, that would be 12 times 9. Well, 12 times 9 is 108, and 27 times 4 is also 108. So those are actually going to subtract, they're technically the same thing. So they're going to cancel out, and we're just left with 2 root 3. So just remember, when you're factorizing these things, try to come up with the highest common factor, such that, so for example, 108, the biggest number which actually goes into 108, which is a perfect square, is actually going to be 36. 36 times 3 is 108. So that the simplest way that can be is 6 root 3. Okay, so 6 root 3 is the simplest that surd can get. So over here, where we've got 3 root 12, well, that can be simplified. 2, 3 times 4 times 12, 4 times 3, and of course the square root of 4 is 2. 3 times 2 is 6. Okay, so that that's interesting, that one. All right, now what we're going to do is just finish on a slightly longer one. So I'll do this with you. Now, first of all, 3, if the square root of 49, you should know, is 7. So it's going to be, that's the same as 3 times 7. Now, what's the biggest number which goes into here? Well, 144 is 12 squared. So if I multiply that by 2, now the square root of 144 is just 12, isn't it? And let's do 2 square root of 18. The biggest number which goes, or perfect square which goes into that is 9. 9 times 2. Okay, so let's simplify this out a little bit. 3 times 7 is 21. The square root of 144 is 12, so that has to come outside. So 12 times 2 is 24. So that's going to be the same as 24 root 2. And then we've got over here minus 12. And, of course, the square root of 9 is 3. 3 comes out the front, so it'll be minus 2 times 3, which is minus 6, root 2. Now, we can bring these together. Well, let's collect like terms. We've got our whole numbers here. 21 take 12 is going to be 9. And how many root 2's do I have? I have 24, and then I take away 6. So that's going to be plus 18 root 2. And now we've simplified that. Let's do the one on the right to finish. What's the highest perfect square? When you're thinking about these, you've got to think about what is the biggest perfect square, whether it be 4, 9, 16, 25, 36, so on. Which is the highest number which goes into each of these? Well, the highest number, we'll go all the way down to, we'll go down to 10 squared is 100. So that's going to be the same as 2 times 100 times 2. Let's do, what's the biggest perfect square which goes into 125? Well, it's going to be 25 times 5. 32's just not going to be 4, it's going to be 16. 16 times 2. And 242, well, 11 squared is 121. So I reckon that would be 121 times 2. Okay, now let's simplify this a bit. So the square root of 100 is 10. Let's bring that out the front. 10 times 2 is 20. So that's going to be 20 root 2. Square root of 25 is 5. Bring that out the front. 3 times 5 is 15 root 5. Square root of 16 is 4, so that's going to be 4 root 2. And finally, we've got the square root of 121 is 11, so that's going to be minus 33 root 2. And look, this is really as hard as it gets as far as I would say for you. Now, let's bring those together. Like terms, those are like surds because they have the same square root. So we've got 24 root 2's. Okay, and then I've got 15 root 5's. Oh, actually, sorry, we're taking away 33. So we've got, what's that? 24 take 33 is minus 9 root 2's. And then we've just got a solitary root 5. So that's going to be plus 15 root 5. Okay, so now I've just been through exercises A and B. Probably fair to say that some of the ones in exercise A will be really more just consolidation. So you should be able to do, I think, if you can do questions 3, 4, 5, 6, and do every second question or just the left-hand side. And then from exercise B, once again, left-hand side, 1, 2, 3, 4, 5. That's what you'll be doing in your working lesson. All right, I'm going to leave you to it, hoping that mostly makes sense.